Okay then, so we're going to have a look at number systems. First thing to note is there's lots of different number systems out there. We're going to look at 3 different number systems: decimal, binary and hexadecimal. What is a number system? It's a way of expressing numbers using digits. Each number system is unique and has a different base. Okay. The base of the number system refers to the number of digits used by the number system. So if we take decimal, which is the number system you're used to, it's called base 10, and that's how you would write it, base 10. And it's made up of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are individual symbols which we have come to understand. If we see this squiggle that looks like a 2, we know in our heads that it means quantity of 2 hands. Right. Now, place order, that is really important. Place order, that is the order in which the digits, symbols are placed, tells us the meaning of the number. So for instance, where a decimal is base 10, so the place order is actually organised into 10 to the power 0, 10 to the power 1, 10 to the power 2, and 10 to the power 3, and so on to infinity. Now what do these mean? Well, if I start to put lines down here, this might be refreshing your memory about what you did in school with cubes, where you tried to organise things into groups of 10, and it was to get you to understand the importance of place order. So what does 10 to the power 0 mean? Well, that means 0 times 10, which happens to be a 1, and it's called units. We know that as units. 10 to the power 1 means 1 times 10, which is 10, the tens. 10 to the power 2 means 10 times 10. 10 times 10 is 100, so that's the hundreds. And 10 to the power 3 is 10 times 10 times 10, which is 1,000, the thousands. So you know this from your past as tens. In fact, units, tens, hundreds, and thousands. Yeah? And you were able to write any number into this system. So for instance, if I had to write 1005, that number would be 1005 units. And what that would be is 1 times 1,000 plus 5 times 1. So that would be 1,000 plus 5, which would equal 1005. That's what's going on behind the scenes. These are things that you take for granted now. If we take another number, for example, let's say 2,374. What's actually going on behind the scenes there is that's 2 times 1,000. Okay, I'm going to put it in brackets, plus 3 times 100, because this is the hundreds, plus 7 times 10 for the tens, plus 4 times 1. So that is 2,000 plus 300 plus 70 plus 4 equals 2,374. The order that these symbols appear in explains the size of the number. If this 2 was over here to the right, then it wouldn't be 2000, it would be 2 units. So it's very important. Now, base digits and placeholder are things that are common to all number systems. So if we take the binary number system next, let's put a line down here to separate that. I'm going to change my pen colour. Let's see, blue. That size there for text, yep. So the base of a binary number is base 2. So it's written, it's called base 2. That means it's only got 2 digits, a 0 and a 1. And this is very important in the world of computing, because it turns out that machine code, the programming language that the actual hardware processor of your computer is programmed in to understand, is written in binary. So every instruction is written in this binary, 0 and 1s, because that's the only level that a computer can understand. And the way the computer uses these 0s and 1s is it translates them into pulses of electricity, and it's the sequence of the instructions that are made up of these 0s and 1s that the computer interprets and understands. So let's have a look at the placeholder for binary. So it's not base 10, it's base 2, so it's 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, let's do another one, 2 to the power 5. So you can see as the number moves to the left, the size gets bigger. So what does 2 to the power 0 mean? Well, it means 0 times 2, which is the 1s column. 2 to the power 1 means 1 times 2, which is the 2s column. 2 to the power 2 means 2 times 2, which is 4, so that becomes the 4s column. 2 to the power 3 is 2 times 2 times 2, that's 8, and that's the 8s column. 2 to the power 4, 2 times 2 times 2 times 2, and that is the 16s column. And the last one, 2 to the power 5 here, 2 times 2 times 2 times 2 times 2, and that is the 32s column. Right, so we can use this placeholder system to work out a number. Now we've only got 2 digits, so in the column is either going to be a 1 or a 0. If a 1 is placed in the column, it means count that. If there is a 0 in the column, it means don't count that. So let's have a look at this. So let's say we want to write out the number 5. Now here's a 4s column, and we've got 0 and 1 at our disposal. So 32 is too big, 16 is too big, 8 is too big, but 4 goes into 5. So that gets a 1, and we take 4 away from 5, and we're left with 1. 2 is too big, so that gets a 0 and 1. And that is equal to a decimal 5. Now, this looks like 101. So to let us know what number system these symbols have been used in, we have to put the base at the bottom of it. So this is base 2, and this is base 10. Yeah, base 10 for decimal, base 2 for binary. So we now know, looking at this, it's not 101, because it's base 2, it's 101. If we had to take this 0 out, because it's got nothing in it, and make it a 1-1, what would happen there is, this is a completely different number. 1 base 2 is actually a 2 plus a 1, so that would be the same as a decimal 3. So the place order is very important, you can't miss it out. Right, last, let's have a look at hexadecimal. Well, now we're not going into a lot of detail with hexadecimal, it's just the basics here to introduce it to you. So what base does hexadecimal use? Well, it uses base 16. And as you can imagine, that's very difficult for humans to get their head round, having to work out base 16, and I'll tell you why. It uses 16 different symbols. So it uses your normal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But after 9 it can't use 10 because 10 is actually made up of two symbols, a 1 and a 0. So it has to go to the alphabet. So it uses A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. So using base 16, F is equivalent to a decimal 15. Right, so let's have a look at how the place order is worked out. Similar to all number systems, this time it's base 16, so it's 16 to the power 0 is the units column. So let's put in units there. I'm going to put a wee line here to separate that. Next comes 16 to the power 1, which is the 16s column. The next column is 16 to the power 2, which is the same as 16 times 16. And if you look that up in your calculator, you'll find out that that's 256. So you can see that it moves very quickly. The number starts getting really big. So from 1 unit to 16s to 256s. But it is possible to represent every number. So let's have a look at how we do this. So say for instance we're trying to make the decimal number 15. So 16 is too big, so we know that we're in this first column here, and we know that we've got these symbols available to us, going from the smallest to the largest, and in this case 50F is equivalent to decimal 15. Now F, we need to put the base 16 under it to let you know that this is a hexadecimal number. This F represents a hexadecimal number, not an alphabet character, and it's equivalent to 15, so we'll put a 15 in there, and that's base 10. So let's look at a bigger number. Let's say it's 33 that we want. How are we going to represent a 33? So what we can do here is, well, 256 is too big, so we're not using that column. But 16s, how many 32s can you get in 16? So we say 16 into 32, that goes twice, and there's nothing remaining in this one. So we have to put a 0 into the units column because we've not used any units. And 20, base 16, tells you that this is a hexadecimal number equivalent to 32. If we had to say 2010, then we know that to be 20. And we couldn't do a 20 base 2 because there is no symbol 2. If we want to see the equivalent of 32 base 10 in the binary system, then we would put a 1 there, but we would need place order, so we would need a 016, 08, 04, 02 and 01. So this is the equivalent of 32 base 10. Interesting stuff.